So good morning. Welcome to the 2015-2016 season of Primetime. Primetime at the Bethel Library is a celebration of the experiences and accomplishments of Bethel faculty, students, and staff, and is a collaborative project between the Friends of the BU Library, faculty development, and other offices on campus. Most presentations are recorded and can be found in the BU Digital Library. Be sure to check the library's news and events page and the BU calendar for what's coming up on schedule. Join us on Thursday, October 1st, as we welcome Dr. Scott Winter, Assistant Professor of Journalism, and celebrate his newly published book, Nebraska Ball, Coach Tim Miles and the Big Ten Team on the Rise. Today we welcome Tyler Miller, Philip Gibbens, Ben Visness, and me. I'm Nathan Gossett. So they're the members of the winning 2015 COMAP Math Modeling team, and they'll be sharing about the competition and the problem that they chose to model, which was if you lose a plane in the middle of the ocean. So I've been asked to give a quick introduction to the competition itself. So the competition that they won is the COMAP Mathematical Contest in Modeling, which people oftentimes wonder, well, what is math modeling? So it's not posing for pictures. So math modeling is basically a system where you're looking at a problem and you're trying to come up with a mathematical formula to describe the problem, and so you're trying to identify what are the parameters that might be impacting the outcome of this problem, and you're trying to use the model that you come up with to predict results before they actually happen. So as a quick example, if you've taken a physics class, we can predict how far a particular object has fallen. If we know what the gravitational constant is, if we know how long it's been falling for, we can produce a model and then use that to predict where that object should be. And we can change the values of those parameters to look at different situations. So where would that object fall, how far would it fall on Earth versus how far would it fall on Mars? So the competition that they were in, they'll tell you more about it, but they basically had 4 days to produce a really good solution to an open-ended problem that didn't have an answer key. And the way that the judging system works is there's 3 levels of triage, where the judges are basically under instructions to get rid of as many papers as possible, because there were over 7,000 papers submitted and no one wants to read 7,000 papers. So at the first level, they basically have about 60 seconds to convince the judges to pass their paper on to the next level. So you can see that a large percentage of the papers were eliminated at that first level. The second level, they might be reading their paper a little bit, looking at the figures, and about 30% more were eliminated at that phase. The third level of triage, they're probably actually reading your paper at that point. And then they were part of the 1/10% of the papers that by the end of the competition were selected as the outstanding winners. And on top of that, they were awarded 2 additional prizes of the Mathematical Association of America Prize for the Best American Paper, and they were also awarded the Frank Giordano Award for the paper that best demonstrated the modeling process. So this is extremely impressive. Just to kind of give you some context here, Bethel has been competing since 2001. This is our 5th win, which there's only been 110 colleges worldwide that have ever won, and we've won 5 times, so we're very pleased with the performance of our students on this competition. And just one other thing that I wanted to point out, I get asked a lot by other coaches whether we actually have a specific course that prepares our students for this competition, since we tend to do quite well. We don't actually have a course that is being driven by this competition, but what we have instead is that the need for mathematical modeling is what caused the creation of this competition in the first place, and that need for math modeling is what drives our curriculum. So a lot of our courses do have woven into the curriculum this idea of math modeling, and that prepares our students to do very well in this competition. So for I'm seeing mostly math people in the audience here, but if you're from a department other than math, I would encourage you to find a competition that matches what your department is already really good at. And there are competitions out there. If you happen to be math, computer science, physics, chemistry, biology, economics, all of these, we're looking for students from those departments to help participate in this competition. It is interdisciplinary, so if you're interested after hearing their talk, please contact me about participating in the future. So at that point, I'll hand off to the guys.
Okay. All right. So, is this working okay? Okay, I'll speak on stage. So, this competition that we did took place over 5 days in February. Well, okay, before I do that, I should say, with this presentation, rather than just talk about the final result that we got, and we're going to talk about our result, but we also wanted to spend more time talking about the process for how we got there. Because I mean, we worked really hard. We had a very short time to produce this. Our paper ended up being 16 pages long, so it was a ton of writing and editing to do. And we had a very short time to do it. It took place over 5 calendar days, but really 4 24-hour periods just by the timeline of the contest. And part of this presentation is we want to highlight missteps that we made along the way as well, because we made some mistakes and had to throw away some work, change some things significantly, but our model was really the better for it in the end. So the very high-level overview of the timeline of our project is that on Thursday, we chose a problem. Thursday evening, we chose a problem and started working on it. Friday through Sunday, we worked really, really hard to produce something. And then on Monday, we wrapped things up and turned it in. So, as I said, the first thing we did was choosing a problem. So there were 2 problems for us to choose between, problem A and problem B. Problem A was a question about distributing a vaccine to try and eradicate Ebola. I don't remember the exact location they said in the prompt, but, and then problem B was a question about how to best find lost planes in open water. And so we had to choose between these 2. We settled on problem B after maybe 5 minutes, yeah. Because, I mean, first of all, we thought that problem A probably would rely on math that only Phil had taken at that point, since, well, we hadn't taken any classes that we thought would really apply to that problem. But also, we all, I guess, just really wanted to do a problem about planes more than a problem about Ebola. So that was, I think, the main reason that we chose problem B. So, I mean, after choosing the problem then, before we dove into the actual modeling process, we wanted to just research and learn as much as we could about the specific plane crash they mentioned in the prompt, and about just, you know, how do planes crash, how do you search for lost planes or lost other objects in general. So we started our research with the specific plane crash mentioned in the prompt, which was the loss of Malaysian Airlines flight MH370, which was very highly publicized, of course, and they never really did find it, although they found some washed up wreckage now, very, very far from the original crash site where they think it went down. But it turns out it's very hard to find reputable sources about this crash, because Google is flooded with copy and paste news articles about this, and it's just horrible to track anything down. However, in a bunch of those articles, we saw references to a report by the Australian government, and then they never cited it, of course, so we had to do some digging, but eventually we did find it. And it was this huge report, probably over 30, 40 pages, by the Australian Transport Safety Bureau with tons of data about what the intended flight path was, where they think it actually ended up, how they were conducting searches, that sort of thing. It was a huge boost to our research early on. We called it the mother load. And the thing is, though, in the end, we ultimately decided not to really look at MH370 at all when we actually made our model. And the reason is basically that MH370 was just weird. It was like the weirdest possible lost plane. Because, and here's just one of the reasons, the main one really, I guess, but what you have there is MH370's intended flight path. It was supposed to fly from Kuala Lumpur up to Beijing, pretty much straight north. It lost communications pretty much right away, and where they think it actually ended up was about half that distance south of Kuala Lumpur. So, like I said, it was so weird, because it basically lost communication right away, kept flying without any location data for hours and hours and hours, and eventually went down somewhere. No GPS or anything really to help, so it was really strange. And so, as we're thinking about this then, we decided we wanted to make a model that would be more generally applicable to lost planes, instead of to just this one really weird one. And from reading it, it was clear that much better research had been done already than we were ever going to do in 5 days, so we decided to leave MH370 alone. Besides that, though, we did just general research about plane crashes and that sort of thing. In doing so, we learned there's an entire field of study called search theory, So that was helpful to learn about because we learned some terminology and stuff that we could use then in our paper. But also, that led us to Motherlode 2, which was another huge report, this one by the United States Coast Guard Office of Search and Rescue, which had just, in addition to like descriptions of search theory concepts, tables upon tables upon tables of data that they had collected based on decades of real-world searches for lost planes and other lost objects. So this was huge because it gave us some like real numbers we could put into our model later to see if we were actually getting feasible results out of it. Over the course of Thursday, we conceptualized 2 math models. Both of these were basically brainstorms, nothing really concrete. But the first version of the model we came up with, version 1 there, we imagined having a circular search area. So we had the center of the circle where we last tracked the plane, and then we somehow come up with a radius of the circle, which is basically how far it could have traveled before crashing. And then we can search that area, but then over time, due to ocean currents and things, drifting the debris around wherever it might go will expand the radius of that circle. And then model version 2 was a refinement of that. Where we kept the same ideas, but then we were also thinking about, how do we search that area? And so we were looking into it and thinking we'll have search planes in the air looking for debris. And we'll have search boats on the water doing like sonar and radar searches to try and find stuff. As I said though, these were not very concrete. We didn't really do any like equations or programming or anything. These were mostly brainstorms. Now, here's one misstep already. On Thursday, we had this idea of expanding the radius over time. But as you can imagine, that will just make the search worse and worse and worse with every passing day. So it's going to be harder and harder to actually find debris. And so we realized pretty early on we really need a better way to handle ocean currents than that. Because we were being very naive. It's like we don't know which way it's going, and so we'll just make the whole area bigger. But that actually ended up being Tyler's focus for the majority of the entire competition. So, and Tyler right now will take you into Friday.
Yep, for Friday morning, we pretty much picked up right where we left off on Thursday doing more research. We found new sources that would help us, and then we also kept reading through the Motherlode 1 and 2 and other sources that we found to really get a good feel for what the research was telling us. One thing that we did find that was really important that morning was a Mathematica Demonstration, which for those of you that don't know, Mathematica is just kind of a software that mathematicians use to help do calculations and visualize things. And this demonstration had real ocean current data from the National Oceanic and Atmospheric Administration regarding the area where MH370 may have gone down. And its purpose was to kind of show graphically and visually how the debris could be moving due to ocean currents. And since it had this real data and it already had a couple useful methods in it, this was one thing that really helped us because we thought maybe we could change this and apply it so that instead of visualizing how the debris will move over time due to ocean currents, we could actually move our search area over time due to ocean currents. And after that, we pretty much met at lunch and we all talked about what we had read about, what we researched, and how we might want to change the model based on what we know now. And we developed what would become our final model, model version 3. And this one, it would do 3 main things. It would create an initial search area, whatever shape we ultimately decided on using for that. It would then move the search area over time in accordance with the ocean currents, and then it would evaluate different search methods that we would program and tell us which one would find debris or the site of the crash the fastest. Friday afternoon, we mainly coded this new model that we'd come up with. We did a lot of coding for the search area, and we continued to develop the algorithm for ocean currents. And by the end of the day, our model was probably about 55% complete. One misstep that we did have this day was how we intended to use search boats. In our original models, we thought about using search planes and search boats, but as we had continued to research, we found that search boats probably would not be effective because the debris would probably be too small for their sonar to pick up, which would be how they'd primarily search for the debris. So we figured it would probably just complicate our model and take up our time and not actually make it any better. So we decided to do away with search rows at this point. And then we got to sleep anticipating that Saturday would probably be our busiest work day.
All right, so on Saturday, we got up knowing that this would be our longest work day of the entire competition, okay? So before we went to bed on Friday night, we all talked about what parts we would all be doing the next morning. So when we got to the room that we were kind of sequestered away in, we all just hopped to it and started working on each of the individual parts. As you can see from the slides here, my job was generally to finish working out the search area generator code, where Ben was going to talk about this a little later, but the search shape that we ended up using was basically looked a little heart-shaped. It's called cardioid. That was the basic search shape. And so my job was to start writing the program that would use the cardioid generating code that Ben would write, and then implement that into a graphical interface that we could use to visually see how our search area was moving from day to day, and how we bound that with the rectangle, and we'll get to that later. That was my job Saturday morning, just getting the code started and working to get ready to integrate their words. Ben, at this time in Saturday morning, he was still working on the debris splash. Now, to explain how that's relevant, remember how I said when we created the original search area, it was kind of like a cardioid shape? Well, something we were thinking about early on was, well, when the plane crashes, you're going to conserve momentum, right? This is physics. And so we were thinking the plane would break apart and there'd be pieces of it that would fly forward, right? And so we were thinking if we wanted to account for that in our model, we have to figure out some way to, formulate that, create a mathematical model of how the debris would splash outward. We don't know where the plane is crashing, but we were assuming that debris would move it out. And so we have to expand the entire search area because of that. So that's what Ben was working on Saturday morning. Tyler was working on accounting for how the ocean currents would drift our search area day by day and change its shape. Because it's not just going to be the same shape day by day. As we all should know about ocean currents is that they aren't all uniform. It's going to swirl around and change the shape. So those were the three different parts that all of us were working on Saturday morning going into the afternoon.
So with this actually, this actually, the debris splash thing ended up being the single biggest misstep that we made the entire weekend. Long story short, we found out that it was actually not going to be significant at all, but basically, I had been researching for hours and hours trying to find data about how this debris would fly, and I couldn't find anything. How big will these pieces of debris be? Is there any kind of data about this, like how fast it would be flying? Would it just and I couldn't find anything, and I was getting desperate. We were like, this has to be important, and so it actually led to some really visually interesting but completely unnecessary stuff, where I actually was so desperate to get data that I threw away all our research and I was using computer animation software that had some physics simulation in it, and I was throwing a virtual cube at a virtual floor and watching it shatter and seeing how the debris flew around, but I depending on how fast I threw it or what angle I threw it at or stuff like that. So like I said, that looks cool, so you can see what that looks like here. So this is not really useful, and I don't think the quality of the simulation was high enough for it to actually give us any good data, but at least it's sort of pretty. But anyway, the problem is then after all that, eventually I went back to research a little bit and looked up some terminal velocity calculations and things and found out that basically we're looking at a search radius maybe of 100 miles or something in some cases, and the debris splash would maybe add about 100 feet to that. So we had to just scrap the whole thing eventually, and so that was I don't know how many hours of my day, at least 5 hours of my day basically just wasted. Several hours of Tyler's day as well, because he was trying to come up with code that would take our search area and add on other shapes based on how the debris would splash around, and we had to just throw all of it away because it was just worthless. There was no change to the actual model because of it. So, but that was like I said, that was the single biggest misstep. But our model was really the better for not having it, because it would have been a bunch of made up numbers that didn't even affect the outcome anyway. So after that whole fiasco, then Saturday evening, our model was mostly complete, but now I was really working on ways of searching this area. And I have a couple of them shown down below. Note that this isn't the fancy cardioid shape that was up there before, but for simplicity, and because we were really running out of time, we instead decided to find a rectangle that nicely fit the search area and search that instead. Just because it made our programming process much easier. So a couple of the primary methods that we used were what we call the parallel search and diagonal search. In the parallel search, it's very straightforward. You have your search area represented in blue there, and your search planes. Remember, we don't have search boats anymore. We got rid of those. It's just the planes. But the planes fly back and forth parallel to the long edge of the rectangle. And we chose the long edge because the planes can only stay in the air so long, and we want to maximize the time that they're spending actually flying over the area and minimize the time they're spending turning around. Now, that same mentality then went into the diagonal search, where we thought, well, how could we get even longer passes over the search area? So, we thought if we turn it 45 degrees to the edges of the rectangle, then it'll be shorter over at the corners, but in the middle of the rectangle, we'll be able to fly very long sweeps over the middle without turning around. So we coded up both of these and left part of that for Sunday. Going into Sunday then, we pretty much just had to finish up the diagonal search, and then I also created an optimized version of our first parallel search because basically with the way that we had put it together, if we had any extra planes that could search the area again, we basically had nowhere to put them. And we needed to take safe flight paths into account and stuff. So I worked on creating this optimized version that would come up with ways to pack more planes into the area in a given day. So that was Sunday morning. After this, our model was really pretty much complete. At this point, we pretty much had all the content in place, and so we just devoted all of our efforts now, focused 100%, all three of us, into just writing this paper. Tyler had already been writing for several hours at this point, I think, since his ocean current stuff was pretty much done. But at this point, Phil and I stopped what we were working on and just started writing and writing and writing, writing and writing and writing, and that took us into Monday.
Yep, and after all that writing, we finally got done pretty early Monday with all of our content, which left us lots and lots of time for editing, which you need a lot of in a 16-page paper. So we pretty much spent hours reading our paper out loud until we lost our voices to make sure it read well, to make sure it was clear and concise, and to make sure that it accurately explained what our model was doing and that all the judges would be able to understand it. We also had a few miscellaneous tasks to finish up on Monday. We had the summary sheet, which is very short, just about a page, but extremely important in this competition because you can have the best model and the best paper, but if your summary sheet isn't good, you still probably won't win. Because in the first round, it's almost the sole deciding factor of who moves on and who doesn't. Your paper won't get read all the way through until later, so if you want to win, you must have a good summary sheet. They also kind of asked us to do this kind of side task, just write a short address to the press, which would be for airline companies that have lost a plane, just explaining to the press how they're going to search for it, just explaining what our model does in non-mathematical terms, and maybe with a couple diagrams. And then we had to spend a fair amount of time just getting the paper turned in correctly, getting all of the files into one big file at the right type, and then emailing it to the specific email address that they gave us to submit our paper. And at this point, we were finally done with all our work, and now we're just going to give you a short overview of what our model that we built over this time actually does. So this is basically now like a very condensed version of the presentation that we did out in DC actually. So just to give you the overview of what our model actually does to find a lost plane. You've heard most of it already, but just to sort of recap. So the first step again is to come up with an initial area to search, an initial area where the plane probably went down. And so as you were saying, this is that weird cardioid, sort of heart-shaped shape, not a circle as we had originally envisioned. And so the basic idea behind this actually is that we know the plane can only travel so far before it hits the water.
But if the plane spends time turning, then after it's done turning, it won't be able to fly as far as it used up some of that maximum distance. And so what we do basically then is we do several small turns in both left and right directions. And so like, you know, here it's like if it doesn't turn at all, it can just fly all of that maximum distance, say it's like 1,000 feet. If it turns 90 degrees, then maybe it could only fly 800 feet after that. If it turns 180 degrees, maybe only 600 feet. And so we do lots of small turns and figure out how far it could go in that direction. And then we put all of that together and we get that nice shape there. And that's very configurable based on all these different things we know about the plane. You know, how the altitude of the plane, how fast it's flying. The wind at the time comes into it a little later on. So we incorporate all of that into this initial area. After that, we use the ocean current stuff that Tyler came up with. Using real ocean current data, we calculate the movement and the reshaping of that search area with every passing day that we haven't found the debris yet. So you can see kind of in the picture there how it could like change over time, especially if one part of it is in a stronger current than the other or something like that. Then another component is that if we do find some debris, we can actually use those ocean currents in reverse to try and track the debris back to the original site of the crash so that we can do a search for underwater wreckage or something like that. That wouldn't have drifted, it just sank. Now, of course, we only have to do the drifting thing if we haven't found anything yet, so searching this area is also really important. As I said before, we find a rectangle that closely fits the area and search that instead. And then we tested out those 3 different search methods that I mentioned in a variety of different search scenarios to see which one would be better. And Phil is going to go over our testing process.
Okay, so now that you've gotten a brief glimpse of how our model works and how all the pieces fit together, and now that you've heard in the process how we got all those pieces, now came the actual part of the competition where we had to test that model. So if you remember how we had those 3 methods developed, we had the parallel search, the diagonal search, and the optimized parallel search, which allows us to use extra planes to repeat the search process, giving a higher probability of detection. So what we had to do, in order to get a wide variety of input settings, like we don't want to just test when there's fair conditions and there's just an abundance of planes. Like that's not always going to be the case. Like you might have to search for it in stormy weather when or it might be fog out that day. So we have to account for a lot of different varieties. So to do that, we actually generated 900 unique input sets, and those input sets were based off of the 4 factors here. The total area that we have to search, and this is talking about the cardioid shape after it's been generated and then moved from day to day and changed by the ocean's currents. Total search area for there. Second one is how many search planes you have in the air going over that rectangular search area for each day. Because probably after the plane first crashes, you're gonna have a lot of planes, but then as search goes on for months or years even, like when you're doing your MH370, you're probably not gonna have 30 to 40 planes anymore. You might have just 1 or 2. And so we need to take that into account. The wind speed at the time of the search. Now this is a more subtle factor, but we still want to account for it. Because as you probably all know from the land of 10,000 lakes, wind makes waves. And so if you have a lot of wind speed at the time you're trying to search, there's going to be a lot of waves. It's going to make all the floating debris, which is generally pretty small, like within the size of a suitcase or a chair here, it's going to make it hard to see from an airplane. The 4th big factor that we tested with these 900 unique scenarios was the visibility. And so this has more to do with how far you can see from the plane when you're flying. So this has to do with the fog, or if it's a bright sunny day, stuff like that. So those are the 4 primary factors, and we generate 900 unique scenarios using a large combination of a huge variety of these 4 factors. Here are the results of what we got. Because we concluded that the optimized parallel would never, ever be worse than the regular parallel, we decided to only really compare diagonal and optimized parallel, but we did do the generation for all 3 methods. Right here, this is a bar graph generating basically the median results, where you have pretty standard search area, you have a pretty standard number of planes. These are the median, the average, most likely conditions that you'll have a plane. So as you can see, the blue graph is the optimized parallel. It's comparing the number of days that it would take to find the debris and track it back versus the diagonal. And as you can see just from the heights alone, it takes the optimized parallel anywhere between 11 to 14 days to find it in average conditions, whereas the diagonal consistently got 3 days in those conditions. As you can see, just having them fly in a straight line, even if they're outnumbered by the optimized parallel, this didn't happen in average cases, but it did happen later. The diagonal was just so much more efficient because it was tracing a straighter route. You could spend more time searching and less time turning. So that was a really cool result. And guess what? The model we made was actually already done by the Coast Guard. And so we didn't know this going into the competition. We found it out like I think a week or so after the competition ended. And this is actually a screenshot of the program that they use. I think it's called SAROPS. Yeah, SAROPS. That's an acronym. I think it's Search and Rescue.
Planning something.
Yeah, programming. It's an acronym. Anyway, but as you can see, the red area that you see in there is their probable search area. Like, you know, red dots mean it's likely to be in this area. You can see it's kind of a circular-ish shape, which is what ours ended up being after we drifted it. You can see that they have a rectangle, and you can see that they fly in a parallel route. And so I thought to myself, oh, they're not using diagonal. Anyway, but it was really cool to see how the model we developed in 4 days was something that the Coast Guard had been doing for years. And so it was really cool to get confirmation of that. A little disappointing, but really cool. Now, going into the post-competition, so that was just 96 hours of our lives, okay? Later in April, we found out that our paper had been chosen as one of the outstanding winners. As Dr. Gossi-Limber said, it's 0.1% of all papers submitted this year. So that was pretty cool, because Tyler and Ben, this is their first year competing, it was only my second, and so it was really, really cool to get the win on first try this. So, on top of the outstanding winner, like Dr. Gossi mentioned, we were also awarded the MAA, the Mathematical Association of America Award, and you already explained what that is a little bit, and the Frank Giordano Award. Now, to explain what those awards are, the MAA Award is basically recognizes as the best paper presented from America, as Dr. Gossi said. And so for that, we were asked to come out to Washington, D.C. and make a presentation similar to this one. It's a bit more on the technical side, like this one's more about the process. But we were asked to present at this year's National Math Fest in Washington, D.C. So that took place in August. And the Frank Giordano Award is an award for the excellence in the mathematical modeling process. Now, this doesn't mean that we have the best models that they saw submitted. Like, it's quite possible that some other paper had the best models used by everyone. But they just recognized that we did a really good job following the modeling process of, like, you know, what we ended up with, etc. All right, do you have any questions? Yes?
So in the paper that you submitted, did you talk about your false starts and what you did to try all of these things, or did you just skip over that stuff?
Primarily we skipped over it. I think we mentioned a few times, but we didn't want to bog down the paper with, these are things we didn't do because they're not going to see them in the results, and so we didn't bog down the paper with too much of that. But it was mentioned a few times.
That would have been more to edit.
Yeah. Any other questions?
So what was the most surprising thing that you learned in your other research, like with the oceanography and rain currents and all those things? What was the most surprising thing?
Are you talking about an individual basis or a team basis?
Either or.
Well, for me, all the MH370 stuff may have been the most surprising, just because like I had no idea how weird a crash it was. I don't know that anything else was really like surprising, and there was a lot of information there, but it was all new to me, so there wasn't anything for me to really be surprised by.
I generally agree with that. It was amazing just to see how much research is done in kind of any field for anything. I mean, there's so much just in search theory and about this topic in general that's been done in math and computer science already. It's incredible what's out there. So that was my opinion.
Yeah, for me, the most interesting thing that I learned from this competition was what Tyler mentioned, the entire field called search theory. Like, I just thought, you know, how do I need to find something? I just kind of look around on the floor for it. There's an entire, like, field of science that gives, like, a mathematical, if you search this area for this long, at this rate, like, it takes, like, 5 different factors into it, you will find it after this long of a time. It's like, I didn't know they had a formula for that. So for me, that was the most interesting thing. Are there any other questions?
I have one more. Do you know how many hours you were awake?
Oh, yes, we do. We didn't write it down, but as we were going through this, I actually kept a log of our major events, like, you know, when we changed models, when we went to lunch, when we went to bed, and everything. I think we got 7 hours of sleep the first night, and then 8 the second, 4 the third, and another 7. So if you add up 7, 8, 4, and 7, 22, right? So 96 minus 22 is maybe 74 hours awake.
We were awake a lot.
And that's a guesstimate.
Oh, and this is just a fun fact about that log that Phil mentioned that he was keeping. So on, I believe the log for Saturday went something like got up, went to the room, and then it's like 9 a.m., resumed work on model, 4:30 p.m., ended work on model. There's nothing else in the middle. That's it, just from one to the other. And like, we probably like didn't even talk to each other much that whole time. We're just like all cranking away at our computers trying to come up with this stuff. So reading that timeline was interesting.
Was all your research online then?
Pretty much, yeah. I don't think we were actually able to find any books or something, although at some point in the degree splash I was considering it, just like, but I don't think we really found anything. That would have been
A lot of the research that we found were actually online manuals, like for search theory. My job, I'm supposed to work on the search theory part and just kind of understand how it works. I found one from the Coast Guard, because it ended up being World War II when it went to where it came from. Like I was just looking at the appendix. There was also another one from fireman training in Sydney, Australia, I think. Third one from the somewhere in Illinois police department on how to search for missing children in a field. And so it's like stuff like this where it was just manuals that we just had to go through and they kind of explain the process.
Our big sources were government sources, so they were freely available.
Speak to the mic.
Did you want to strangle each other at the end?
No, not really, actually. I wanted to sleep.
Yeah.
Yeah.
Yes.
We're rooming together this year.
You said that your final product was similar to the Coast Guard, right?
Yeah.
But did they take any other aspects from your final design? Did they incorporate it anywhere else, or is it just?
Well, I mean, their model was made way before ours. The Coast Guard thing was just something that we learned about after the fact, and we just basically learned that, like, oh, all the ideas that we came up with in these 4 days were ideas the Coast Guard already had decades ago and have been using for a very long time. So, again, like you said, it was kind of cool to learn that, like, oh, you know, our ideas like are valid and like they're used in the real world, but at the same time, it's nothing new actually that we really came up with. Except for there were some things that were new, but in large part it was all new.
Yeah, it was a great model, but some people will dedicate like their entire lives to a topic like this. So it's difficult to really get something new out there.
Anything else at all?
Are you guys gonna try again this year for the competition?
I think we're obligated to it this year.
Do you know what the topic is?
No.
They don't announce until Thursday night of the competition.
Yeah, that's the thing.
Something about the COMAP competition which we didn't really mention was, as Dr. Gosson just said, the questions for that year are posted Thursday night at like 6:50, 6:55, and then the competition starts at 7. And so you have about 10 minutes of, what do I want to do this year? And then you start the competition. So does that kind of explain, help answer your question? All right, well, if there's nothing else, we'd like to thank you all for coming.